Hey everyone, today I'm going to be showing you an air umbrella. So the goal of the air umbrella is it has fast moving air shooting out the sides of it in all directions, and as the rain falls down, it hits the air and deflects the rain away from hitting you. Now initially the air umbrella sounds like a good idea. Instead of having this big bulky umbrella around you, you can just carry around an umbrella stick, turn it on, and then you just have this magic umbrella that comes out over you and nobody can even see it. But then when you get to thinking about it, you might start thinking, well, what happens to the rain when I'm just blowing the rain away from me? That means if there's anybody around me, I'm basically just blowing a bunch of rain air into everyone else's faces. But that's not the point. Let's just worry about number one. So you want an air umbrella, forget about everybody else. Okay, let's take it outside, turn it on. I'll just sprinkle it with my sprinkler right now. 3, 2, 1. Okay, so you can see it's actually working pretty well. You can see as the rain's falling around it, the air is hitting it and pushing it away from the center of the umbrella. Now, I wasn't the first one to think of the air umbrella. In fact, in 2016, there was a Kickstarter and it earned $102,000 from a company claiming that they would make the world's first air umbrella, the handheld air umbrella that was powered by a battery that could shoot air out fast enough to blow the rain around you so that you didn't get wet. But they never delivered on their product. So what problems did they run into? Why were they never able to deliver the air umbrella? And how did I make my air umbrella? Well, let's do a few calculations and figure out how fast we need air to be going to be able to blow raindrops away. So the easiest way to do that is figure out the average terminal velocity of raindrops. When raindrops are falling through the sky, they don't just keep accelerating until they hit the ground. They keep accelerating until the wind is hitting them so fast that eventually they stop accelerating and they reach a constant velocity. That's their terminal velocity. And any falling object will reach a terminal velocity. Now, using 2.5 millimeter drop diameter, I calculate that you get around 8 meters per second of a terminal velocity. That's around 18 miles per hour. So 18 miles per hour is our terminal velocity. So that means to at least get a 45-degree angle deflection like this, since our raindrop's falling and hits the airstream right there, if it's going to completely get deflected at a 45-degree angle, since it's still moving down, it has to move that direction at least at 18 miles per hour. So the air has to at least be coming out of those slits at 18 miles per hour, but it actually has to be coming out even faster because it takes some time to speed up the drop in that direction because it doesn't immediately start getting pushed that direction at 18 miles per hour. So you'd have to flow this faster than 18 miles per hour to get at least even a 45-degree angle as the raindrop's falling down at terminal velocity. But the problem is, as you move further away from the pole, you have a much larger area that you're needing to flow all of that air. And so that means that you have a lower velocity overall. And so in order to keep the velocity up, you have to increase the volumetric flow rate. So you need a huge airflow at the beginning to have high velocities far away from the center of the pole. So if you didn't follow any of that I was saying, just get this. In order to push rain away from you, you need a whole bunch of air coming out of these holes here. And the problem with that is, in order to push a lot of air, you need a really big motor. So how much air am I talking that you need to push? About a leaf blower amount. And that's exactly what I did here. I just connected my leaf blower to it, and even at those extreme high velocities and really high flow rates, you can see that only deflected a tiny trickle of water. And you can see that it didn't deflect it that far, maybe about this far from the center of it. And so when I tried to use it for myself, putting it above my head, I still got pretty wet. Unless I held it about right here, I got soaked everywhere else. So I was able to keep it mostly off my head by putting it really close like this. So would it have been possible for this company to actually make a product that was a handheld device that you could blow that much air out of? The answer is no. There's no way they could have done this. And what's interesting about this Kickstarter is I've actually seen the device advertised on different news channels as if it's a real device that actually exists. But you can see from this experiment, unless you get some super powerful batteries and a super powerful motor, you're not going to get much deflection of rain. And even if you can deflect the rain, I don't think anybody's going to be wanting to walk around you when you're blowing a bunch of rain in their faces. And thanks for watching another episode of The Action Lab. I hope you enjoyed it. If you did, remember to subscribe and hit the bell so you can be notified when my latest video comes out. And thanks for watching, and I'll see you next time.